Hey everybody. Yesterday an article came out that talked about how a new kind of photosynthesis has been discovered. Now, this is really exciting, but if you don't spend all of your life steeped in photobiochemistry, the article was a little bit unclear on what photosynthesis is uh, in the level of detail that you need to understand what this new finding is and why any of this matters. So I thought I'd just take a second to explain all those things so that you can understand why this is so exciting and what it actually means. So the first thing you got to understand is how photosynthesis actually works. Throughout school we all learn that light comes into plants and they grow. They photosynthesize and they make their own food, and that's true. But the way that actually happens is that light comes in, and plants can utilize all of the light that are the appropriate level of energy, right? So for plants, that's really everything kind of in the visible spectrum. And the light comes in, and there are all these different pigments in plants. You've probably heard of chlorophyll. So there's chlorophyll A and B, and then there are all these secondary pigments. So there are a bunch of them, but there are carotenoids and there are xanthophylls, and there are subclasses of all those. But these different pigments all kind of handle different wavelengths differently and let the plant harness energy from all of them. Now, when you have wavelengths beyond that, they're longer and they have less energy, and they're just not enough energy. They're not energetic enough to do anything. So maybe they warm up the plant a little bit, or maybe they actually cause the plants to fluoresce a little bit. That's really hard to measure, but it happens. And then on the flip side, if you give plants photons that are too high in energy, so UVB, UVC, X-rays, gamma rays, these are things that they rip apart all of the photosynthetic machinery. They just over-energize things, and it's bad news for a whole lot of reasons. But the punchline is that it kills the plants. So with this new kind of photosynthesis, there's a new pigment. It's called chlorophyll F. And what it can do is it can take these wavelengths that are really low energies, specifically infrared radiation. Normally, this is just heat. But with this new chlorophyll, it can take that energy and it can energize that whole system, and an electron will get kicked off and it goes to do photosynthesis, which is how plants actually end up making all of their food and carbon tissues and so on. So that's a pretty big deal. But the more exciting thing here is that before, when I was saying that ordinary photosynthesis gets ripped apart by higher energy photons, that would probably lead you to believe that with this new kind of photosynthesis, if you don't give it these really low energy photons, if you give it visible light, it's going to have more energy, and consequently, it should rip that system apart. And the best way to think of this is, if normal photosynthesis is kind of like a trampoline, and all of the pigments, so the chlorophylls and the carotenoids and xanthophylls, those are all the parts of the trampoline. So you have your metal legs and you have the metal springs around the side, and you have that rubber material that makes up the main sheet. That's all of the machinery to make normal photosynthesis happen. And then we are like visible light photons. So we come along and we jump on the trampoline, and when we jump on it, that energy that we've imparted into that system gets absorbed by the legs and the springs in that sheet, and it can handle it and it bounces us back up. That's kind of like photosynthesis happening. This new kind of photosynthesis, though, is almost as if a fly came along and it's buzzing around and then it lands on the trampoline. It doesn't have enough mass or energy to cause anything to happen. As far as that fly can tell, you're not on a trampoline. And as far as the trampoline can tell, nothing has touched it. Now, this new kind of photosynthesis is a lot more like a spider web, right? Where if we walk through it, we just rip it apart. I mean, we're probably not even going to notice most of the time. But if a fly is flying around and it hits that spider web, obviously it's going to cause it to bounce in the air, and it's going to cause it to vibrate and all these things. It's certainly going to be enough energy to let the spider know that something's going on. It's going to come along and do what spiders do. In this analogy, that's like the new kind of photosynthesis. Now, the really interesting thing is that with this new kind of photosynthesis, that whole analogy of us walking through the web doesn't happen. So if you take the new system and put it in visible light, it doesn't get ripped apart. So what does that mean? Well, if you extrapolate this just to the idea of harnessing energy, for example with solar panels, it means that there's a way to capture more light energy without destroying the whole system. And it isn't a huge amount of energy because these are long waves, but it's still there and it's still constant, and there's a lot of it in our atmosphere. So, to make another analogy, if you imagine a bowling ball rolling down a bowling alley and then firing a ping pong ball at it, right? That's like this long wave energy where it doesn't have a lot itself. But if you fire infinity ping pong balls at this bowling ball, eventually that'll slow it down and stop it. So it's a situation where if we can capture even a little bit more or a little bit broader a region of light, that can have pretty significant impacts. So that's why this is really exciting. And just as sort of a photobiologist, it really makes me have to think about things in a new way. Things I've been studying for about 10 years. I have to look at and go, okay, well, maybe this doesn't work the way that we thought it did. So that's all. I hope this was interesting. And, if you have any questions, feel free to ask. See ya.